exponential form of that is the a is the base, the y is the power, and then that equals x. That's what a logarithm is. And that's why it's called the inverse function, because we were just talking about a to the x, weren't we? Now we're talking about a to the y equals x. So you see that's what an inverse function does. It switches the roles of x and y. But anyway, just to give you a little more example here. If I'm looking for the log base 3 of 81, I don't know that we'll have to find these logarithms, but the way we go about teaching it usually is we say, well, convert that to exponential form, and that says 3 to what power is 81? And that's what that value of that logarithm is. What power of 3 gives you 81? It's 4, yeah. 3 to the 4th is 81, so that's why the logarithm there is 4. We also have the natural logarithm, ln. Is the way we designate it, ln of x, ln of some number. The natural logarithm is just the logarithm base e. E's not showing as the base here, but that's what it's understood there to be, for the base to be. It's logarithm base e. ln, they don't put the e there because it's understood to be e, okay? They don't want to write the e. And then the other one, possibly that would come up, well, I don't even mention here, so there's the common logarithm. It's logarithm base 10. But I haven't mentioned here, so I guess that doesn't really come up. One other thing that might come up that's kind of related is it's called the change of base theorem. Oh, I didn't mention it, but the good thing about the natural logarithm, common logarithm, is those you have on most calculators built in. You have a natural log button or a common log button. So you can do the ln of any number. And so that's why those are preferred. This change of base theorem gives us a way to convert. Like if I want the log base 2 of 58, well, that's 2 to what power is 58? That's not a nice power of 2. However, with this change of base theorem, what it says is you can change the base to natural log or anything you want it to be, but here's the way you do it. You do the natural log of 58 divided by the natural log of 2. And that may, I guess I should have wrote, the change of base theorem is log base a of x equals ln of x divided by ln of a. So you can do that with any base logarithm, because that gets it to common logarithm, natural logarithms. You do the same thing with common logarithms too. We may use that. All right. Well, turns out that the derivative of logarithms, the first one, we'll start with the natural logarithm here, and you can look at the book for proof of this, but I don't have a real nice way. Well, we can think about it. All right. Yeah, it turns out the derivative with respect to x of ln of x, turns out that's pretty nice. Even though it's a logarithm, and logarithms have all kinds of complication. Turns out it's really pretty nice. It's 1 over x. Like I said, there's proof of this going through with the definition of derivative, but lack of time, and we can explore other things. Yeah, it's derivative of ln of x is 1 over x. Now, one thing let me, I guess, highlight here is we can go to, like if I graph the ln of x, and like I said, you can type it in your calculator there, but any logarithm kind of has that sort of curve to it. It's kind of hockey stick, I call it. The exponentials, I guess, are more what I call a hockey stick, but this is an inverted hockey stick. But, I mean, it's an infinite hockey stick, but it goes infinitely both ways, but hopefully you see what I mean. The reason I mention that is because if you look at 1 over x, of course, in logarithms, x can't be when it's ln of x can't be 0 or negative. So that's why we only have this side. 1 over x, the x could be positive or negative, but if you look at the right-hand side of 1 over x, you can kind of see, if we think back through some derivative stuff we talked about on the graph, the derivative is the slopes, right? What happened to the slopes here? Well, the slopes are very steep, a large positive here, and then what? They progress and get less steep. Isn't that what 1 over x here does? Real steep, and then progressively gets smaller. And the other thing is they're always positive. You see that? Always positive slopes. We don't have any negative slopes. And that's what 1 over x has for x greater than 0, which is what we said we have to have. That's the domain of that anyway. So you can kind of see that it works. Just by looking at that, that's not proof of it or anything, but helps us to remember some things there. Well, that's good news because, yeah, ln, the derivative is just 1 over x. If I have a more complicated ln, like ln of x squared plus 5x minus 3, what do you think there for derivative? Well, this one's a little better than the exponential because it's fairly obvious you've got an inside and outside, right? The outside's the ln. The inside is x squared plus 5x minus 3. So I've got to do chain rule. All right, so what's the derivative of the ln? Well, ln of x is 1 over x. What would the derivative of this ln be? 1 over the inside part. So the ln part, the derivative is 1 over the inside part. But because of chain rule, now what do we multiply by? We got to do the derivative of the inside, right? So you got to do the derivative of x squared plus 5x plus 5. And they would probably squeeze that because that would just be 2x plus 5 over x squared plus 5x. That's my derivative. Okay? Yeah, let me mention this because of one thing that happens, just to show you as far as simplifying goes, because I'm pretty sure it comes up in the homework. You see it. That is this one. All right, so say we got y equals ln of 3x over x minus 3. What's the derivative? Well, okay, same deal. Got the inside and outside. The derivative of the ln would be 1 over that. Right? Times then, well, the derivative of the inside would be quotient rule. So it'd be low times the derivative of the high, which is 3, minus high, 3x, times the derivative of the low, which is just 1, over low squared. Okay. this is going to work out much better than this. Well, one of the reasons I show you this is because this means 1 divided by 3x over x minus 3. If I write it like this, maybe a little hint as to what we can do with that. Isn't that the same as 1 times the reciprocal of that? Yeah. So this is just x minus 3 over 3x. Okay. Now, of course, there's some simplifying here. That would be 3x minus 9 minus 3x. So I'm going to cut to the chase here. 3x are going to cancel. So that's just going to be negative 9 over x minus 3 squared. Okay? Now, what else can we do? X minus 3 can cancel out because there's 2 x minus 3's there. So we wind up with negative 9 over 3x times x minus 3. So, yeah, some of these, they can, again, it's algebraic stuff. So, oh, well, there's even more there because look at my paper and saw that we can also do this, cancel it. So we wind up with negative 3 over x times x. Okay, now, here's something we can extend our derivatives of the logarithms a little bit, and it comes via, that's why I mentioned that change of base theorem. Here it is. Let's say we got a log base 2 of x. Well, we don't know what that derivative is right now, but let me do it this way. All right, so let's say we've got, so I'm looking for the derivative. Let's just say we do one in general. This kind of, sort of a little mini proof here. By the change of base theorem, I can change that over to natural logarithm because I know about the natural logarithm derivative, right? So if I had this in natural logarithm, I can do that. What's the change of base tells me log base A of x would be ln of x divided by what? ln of a. Change of base theorem. Now if you look at that, a is just a number. This is just 1 over ln of a times ln of x. This is just a number. You don't have to do quotient rule because that's just a number. That's just a number. What's the derivative? Well, if that's just a number, you take that number, 1 over ln of a, times the derivative of the ln of x. 1 over x. So, the derivative. So the derivative is 1 over ln of a times x. Usually you write it as 1 over x times ln of a, so you don't get confused what's in the ln and what's not. See what this means? Back to this. So y equals log base 2 of x. The derivative then would be 1 over x times the what? ln of a, what's a here? 2. A is 2, so it would be 1 over x times ln of 2. So, moral to the story is, if it's a different base other than natural base, the derivative is 1 over x, but you have this extra little piece. You got to multiply by the ln of the base. See that? Okay. Now, this also gives a way to revisit our old friends, the exponentials. Now start here with this. There's a little cancellation property of logarithms. If you've got a, and then you raise that to the same logarithm, or to the logarithm of the same base, does anybody know what happens? Since they're inverse operations, I've got a to the power of log base a those cancel out. That's just x. So e to the ln of 6, same idea. The e and the ln, those are inverses, so those cancel out, so you just wind up with 6. Why do I mention that? Well, if we look at, okay, so here's why I mention that. Let's say I've got a to the x. I can rewrite that. It's kind of going the other way here. I can write that as e to the ln of a to the x. Right, because doesn't this simplify just to be a? Very same idea. I guess I could have done, I did 6 here, but maybe I should have just done a. E to the ln of a is a. So it cancels to that, but couldn't I just go the other way and say we could write a this way? Okay, that's what I do here. All right. Now then that is then just e to the ln of a times x. So a to the x is equivalent to that. If you buy that, then we can proceed here. Here's where I'm going with this. So back when we started our talk here, we said when we did the derivative of a to the x, this derivative was a to the x times some constant, right? I'm going to show you what the constant is by a little process, using this little kind of process right here. To figure this out, because I don't know what that is, but I do know how to differentiate, do the derivative of an e to a power. That's just chain rule. Okay, so by what we just said, I can rewrite a to the x as e to the ln of a times x. Now I'm doing the derivative of e to a power. How does that work? Like we just said, the derivative of e to a power is e to that power times what? Times the derivative of the power. Well, the power is ln of a times a. ln of a is just a number. Because I'm going to know that a is just the base, whatever the base is. This is just a number. A number times x, what's the derivative of a number times, what's the derivative of 2x? Derivative of 2x is 2. Well, the derivative of ln of a times x would be ln of a. Yeah, ln of a. Well, that's great, but get it to what I need here. Okay, well, now reversing back, e to the ln of a times x, what does it equal? It's a to the x. Ta-da! That turns out that constant is just the natural log of the base. So now we can fill in the rest here. Okay, so if I've got y equals 2 to the x, then the derivative is going to be 2 to the x times the ln of a, well the a here is 2, so it'll be 2 to the x times ln of 2. So that constant turns out it's the natural log of whatever your base was. So that's not too bad. I mean, it's not as good as e to the x. The derivative of e to the x is e to the x, straight up, but it's about the next best thing, I guess. The derivative of 2 to the x is 2 to the x times the natural log of 2. And of course, almost here, done here. 3 to the x would be 3 to the x times ln of 3, yeah. What about two more? One more. I'll finish up with this one. All right, so f of x equals 8x squared minus 4 then. What is my derivative? Okay, well, we've got 8 to a power. It's just that the power is just not simply x. If it was 8 to the x, it'd be 8 to the x times ln of 8. But it's 8 to the x squared minus 4. Well, guess what? We have to use here what rule also kicks in. It's a chain rule. What it amounts to is, yeah, we've got to do the ln, we've got to do the derivative of the 8 to the power, and then we have to do the derivative of the power. Now, a to a power, an x power, well, the derivative is very similar, except it's not x, it's x squared minus 4. So, help me out here. What do we start here? Well, if it's 2 to the x, it's 2 to the x times ln of 2. It's 8 to a power, so it'd be 8 to that power times ln of 8. But then I have that extra component because I have that power as x squared minus 4, so I've got to do the derivative of it. The derivative of the power, just 2x. It's a chain rule. Is that okay? Is there anything, there's nothing really there. I can't combine the 2 and the 8 or the 2x and the 8. That's it. Okay? It's not a simple, I guess, derivative, but it's what it is.